Hi everybody, so in this video we're going to take a look at metallic bonds, and we're going to use this really nice diagram from Klein and Dutrow that explains not just metallic bonds, but a theory that was developed to explain their behavior, a theory called band gap theory. So the thing about metallic bonds, their key characteristic is that electrons, let me just abbreviate that as an E minus, electrons are not localized. They're not localized about a particular nucleus. And that has a huge impact on how the electrons behave in a given material. They're free to move out from one atom to another. So in this leftmost diagram, they illustrate the idea about how this works. So we have energy increasing up towards the top of this part of the diagram here. And then we have distance. Atoms that are very distant, that are very far apart, their electrons are going to occupy very, very discrete energy levels. But if you have two atoms, let's say one over here and another over here, then those electrons begin to see one another, begin to interact. Those interactions affect the energy levels. They affect the energies in the various electron orbitals that the electrons occupy. And that's what's shown here. You can see the energy being spread out to the point where those energies can overlap. So over here, where the atoms are distant, the 3s and the 3p orbitals are very distinct in energy. But over here, where the atoms come into contact, or at least very close proximity to one another, the available energies begin to overlap. In this diagram here, they're showing that instead of talking about a discrete energy level, you could talk about a band, a range of energies. So that's where band gap theory is a little bit different. Electrons now have not a single energy assigned to them, but they can occupy a range of energies. And it's that range of energies that allows them to drift around from one part of the structure to another as they go from one orbital to another. So in this case, for example, they're looking at the 3s band overlapping with the 3p band. So you might have an element like magnesium, and it has two electrons in its third s orbital. Well, it has no electrons in the p orbital, so we can write 3p, and that would be a 0. But those p orbitals, if you bring two magnesiums in close proximity to one another, let's say that's a magnesium and that's a magnesium, now those energy levels in the p orbital become available. So you have an overlap. This is the valence band, so these are the valence electrons that are available for bonding. And they are going to be able to go into the p orbitals, and as they move around, it forms this conduction band. And that's what allows these fellows to drift. Now, in the rest of this diagram, they're comparing the characteristics of things that are metals or semiconductors or insulators. So with a metal, you have an overlapping band, and so it's easy for electrons to go from one orbital to another. For a semiconductor, you might have a small band gap. So if you add a little bit of energy, then an electron can hop from this band, up, valence band, up into a conduction band. So without that energy input, it would be an insulator, but add a little bit of energy and it can become a conductor. And then if you have a large band gap, then the electrons that are floating around down here, they're just not going to be able to make that leap into the conduction band, and those things are not going to act as conductors. So that explains some of the characteristics of metals. So for metals, they're going to be very good conductors of heat and electricity because that band gap is closed. Whereas for more common rocks and minerals, there's a significant band gap, and so they're not very good at conducting heat or electricity.